In this video, I want to discuss something called the kernel and image of a linear map between vector spaces here. Okay, so this is our goal here. We want to try to describe and understand kernel and image of a linear transformation. Now, these ideas are going to be very similar to what you've seen before with something called the range or column space and the null space, okay? But not respectively. Okay, let's go ahead and look at a definition of ours. Okay, let's say V and W are subspaces of Rn. Okay, and T is a mapping from V into W, and it's a linear transformation or a linear map or a linear operator. Any of those terms will work, even a linear function. Okay, but it's a linear map, linear transformation. Okay, let's talk about the image of T. The image of T is defined and denoted in the following way. So I've got just Im of T. Okay, this is the way your book does it. It's a set of all W bar such that what? W bar is T of V bar for some V bar in cap V. Okay? You could think of this as being then what? Actually the range, okay? So you could think of that as being the range of T, all right? All right. How about the kernel? The kernel of T, that's K-E-R-N-E-L, okay, kernel. The kernel of T is defined and denoted by the following way, K-E-R of T, so that's the way your book does it anyways. So this is a set of all V from cap V here. I might have thrown that in, such that T acting on V bar gives you the zero vector in W. Okay, but W is actually a subspace of Rn, so that would actually be the zero of Rn. Okay, all right. So this is what? This is the set of all the vectors in V that get mapped to what? The zero vector. Okay? That's what we call the kernel of the transformation. Okay, so it sounds a bit like something we've seen. You remember null spaces of what? Of a matrix. Okay? And you know there's a great relationship between linear operators or linear transformations and matrices here. So these ideas are definitely connected here. But let's go on. Let's give you a quick proposition here. Okay? The image of T is a subspace of W, and the kernel of T is a subspace of V. Okay? So this is saying the range is not only a subset of W, which is obvious, it's also actually a subspace. So that means it's going to be what? Closed under linear combinations. Okay? Now, obviously, also, what? The kernel would be a subset of V, cap V there, but it's actually also a subspace, not just a subset. So it, too, its elements are closed under linear combinations. Okay? Now, let's go ahead and see why that's true here. Okay? Suppose I've got two vectors. I called them W1 and W2 bar. Okay? Suppose those are both elements of the image of T. Okay? If that's true, then there's got to be what? Pre-image vectors, say V1 and V2 in cap V, such that T acts on V1 giving W1, and T of V2 gives you W2. Okay? Those are kind of sloppy there, but that's because I had them turned around originally. But anyways, okay? So these are the pre-image vectors, okay? We're not necessarily saying they're unique or anything like that. We're not saying this is one-to-one now or anything. It doesn't matter. Okay, but anyway. Now, for any scalars A and B, so I'm just talking about real numbers in essence then. Okay? This linear combination, A V1 bar plus B V2 bar is going to be an element of V, right? Because V is a vector space, right? It's a subspace of R to the n, as a matter of fact. Okay? So, if I go like this, T acts on that linear combination. Since T is actually a linear operator, you see I can break it up this way. That's A times T of V1 bar plus B times T of V2 bar, which is what? A of W1 plus B W2 bar there, okay? That's obviously an element of this because what? I'm mapping some vector in V by T, right? So that's got to be part of the image of the transformation there. So this is obviously part of the image of the transformation. So this thing is part of the image of the transformation. That's a part of this setup here. So notice this then. If these two are in the image, then what? That arbitrary linear combination is also in the image. That makes it what? A subspace. Okay, a subspace of W, in fact. All right? All right. Now let's go ahead and deal with the kernel. Now suppose that I've got a couple vectors in the kernel. I'll call them V1 and V2. Okay. I don't always say the bar. Maybe I should. V1 bar and V2 bar, but sometimes I forget. But you can see it here. Anyway, so they're arbitrary elements of the kernel. Okay? So we know that they both get mapped under T to what? The zero vector. Okay, the zero vector here. Okay? I guess that's coming off the screen just a wee bit here. I wonder if I can... do that. Maybe that's a little bit better for you. Okay, sorry. Anyways, now I take arbitrary scalars once again, so these are just a couple real numbers here, and I just think about taking T of their linear combination. Okay, oops. Okay, well you know T of the, because T is a linear operator, it's going to do what? It's going to act upon this linear combination this way, so I can break it into a sum, right? And then I can take those, what? Those scalar multiples on the outside of T. But each of these is equal to 0, so that's A times 0 plus B times 0. That's going to have to be the zero vector. Okay? Wait, so that means that linear combination actually has to be part of what? The kernel, because the kernel is all vectors in V that get mapped to 0. Okay? Thus, the kernel of T is a subspace of V. Alrighty? Alright. Now let's just mention these ideas and definitions apply in the more general case that V and W are general finite dimensional vector spaces and not necessarily, as we assumed above, subspaces of R to the n, or Rn if you like that better. Okay? Alright, so you can generalize those ideas. Okay, I mentioned that because your book does an example here. They immediately jump in where one of the subspaces is not technically a subspace of R to the n. They're not both subspaces of the same vector space. But let's go ahead and do this one here. I don't usually do examples from the book because they're already in there, but I want to take a slightly different viewpoint from what the book did. Okay, so you can compare and contrast with the first example they have. Anyways, here's a following linear operator here, okay? Linear transformation or linear map. T goes from R4 into R2, okay? Now, by the way, when we say into R2, that doesn't mean it might not also be onto, okay? It's just if you don't know that ahead of time, you would just say into, okay? Anyways, this is how it works here. T operates on what? A, B, C, D, an arbitrary element of R4. It returns the following two vector, A minus the B, C plus the D. Okay? All right, so that's what it does. Now, let's just prove that this is a linear operator. What's an easy way of proving it's a linear operator rather than going back to the definition? Okay, and going through a set of, they make sure all the steps of the definition are satisfied, is to just what? Show that you can write this as what? A matrix product, right? Okay? All right, so if I've got this vector A, B, C, D, and I've got a matrix I'm going to call A here over on the left, okay? Notice that the following matrix will do. Reading across, 1, -1, 0, 0, 0, 0, 1, 1, okay, by A, B, C, D. Do you see when I multiply these two, this 2 by 4 vector with this 4 column vector, that I actually end up with what? A minus B, and then what? C plus D, that 2 vector. Okay, it works. Okay, now I'm going to throw this in here. I'm going to mention, this is what your book didn't do. They didn't show it as a matrix product. So I'm taking that slightly different viewpoint. I want to mention here already this matrix A corresponding to T transformation is already in row reduced echelon form. Okay, I'm just going to mention that here because I'm going to state a couple things. I claim this the kernel of T, right? Those are all the vectors in R4 that get mapped to 0. Okay, I'm claim that this is going to be the same as the null space of A here. Okay, remember what the null space of A would be, right? Okay, it would be the set of all 4 vectors being mapped to 0 under what? Under this multiplication, right? Okay, but that corresponds to our transformation, so that's essentially what we've got here. Okay, now I've labeled the columns for convenience here, A, B, C, D, and then I wrote it as an augmented system here, so I've got A over on this side, and those are there's our A matrix, and then I've got zeros on the other side because we're dealing with the kernel, right? All right, vector is getting mapped to 0, the 0 vector, okay? Notice here that the rank of this matrix is actually 2. Again, I already said it's in row reduced echelon form. The free variables would be what? B and D, because the pivot variables would be what? A and C, okay? But you remember when we solve problems like this, what we typically will do was what? Solve everything in terms of the free variables. So here I'm going to solve everything in terms of B and D. Okay, you would see the first line would imply that what? A equals B, and the second line that C is minus D. So writing the A and C in terms of B and D respectively there. Okay, so this is what it looks like here. So my 4 vectors in the kernel of T, or the null space of A, okay, would be what? B, B, right? Since A is B, so those would both be B's. The C is minus D, and then the D is D. Those are free. So you've got what? 2 free parameters here. This is going to be 2-dimensional. The kernel is going to be what? 2-dimensional also. So the kernel is going to have a dimension of 2. Okay? You can see I actually write it this way as this linear combination of these 2 vectors. So 1, 1, 0, 0, 0, 0, negative 1, 1. These are a basis for the kernel of T. Okay? So we would say the kernel of T is just the what? The span of those 2 vectors, which is in essence what letting B and D up here range throughout the real numbers. That will give you the span, right? Okay, so there's the kernel of T. All right, now let's talk about the image of T. The image of T is actually going to be the same as the column space of A. Okay, remember the image of T is a set of all vectors you would get out of this thing, right? So that would be what? A subspace, we said, of R squared. Now it might be the whole space. Maybe this is onto. That was my comment before. Okay, when I copied this, it sort of chopped the bottom off. I'm sorry about that. But anyway, again, this matrix A that we were dealing with, I'm just showing this in parentheses here. This matrix is in already row reduced echelon form. Here I've got what? I've got the pivot columns labeled here with my arrows here. Okay, so remember this is going to be the same as the column space because all I'm doing is considering linear combinations of these various columns up here. Okay, that's in essence what I'm doing. So this is going to be the same as the column space of A. Okay, you can see here, because this is the same as the original vector, or the original matrix, I didn't actually change anything on here. The 2 original, see this is what? The first column and the third column. If I go back to the original, which is just exactly the same as what I have down here actually, that's not always the case, you remember. I would have what? The first, column and the second column of the original, and the span of those two would give my column space. That's going to be exactly the same as the image of t. Notice, since that's 1001, that's our standard basis, so I've actually got that written in there. This is what? R squared, or R2. Okay, so the image of t is actually R2. That means this map appears actually not just into, but onto. Alrighty? Alrighty, I'm sorry that got cut off there, but anyway. Alrighty, let's keep going. Here's a little theorem for you. It's a simple exercise, okay? We've actually seen this kind of thing before multiple times. Let t be a linear transformation, okay, such as above. T is 1 to 1, and only if the kernel of the transformation consists of the zero vector alone. So it's that trivial vector space, okay? Just the zero vector. Okay? All right, so that's an EFY. What is that? Exercise for you. It's pretty trivial. It's pretty easy. Okay. And that's for one-to-oneness. Okay, that's my lazy man's one-to-one. All right, let's go on to a different theorem. Let T map V into W. Okay, that's a linear transformation, so it's got to be linear again. It's not just some crazy transformation. V and W are subspaces of R and again. Okay? Suppose the dimension of V, okay, your original space here that you're mapping from, your domain space, if you wish, the dimension of that is M. Then what we're going to show here is that the dimension of the kernel of T plus the dimension of the image of T adds up to M. Okay? Your book has a couple typos in here. They state the theorem correctly, but then they keep replacing the M by N in examples below. It should be M everywhere in their discussion. M. Okay? Not N. They had little typos there. Okay, let's give a proof of why this holds here. Okay? Let's go ahead and let U1 through UR, okay, be a basis for the kernel. Okay? So these elements are actually coming from what? Coming from V, right? Okay? U1 through UR. Okay? We know this is a space, right? This is a subspace of V. Okay, so it's a subspace of the subspace of R to the N, or Rn. Okay? But, so it has some sort of basis, and this is it, right? Okay? So every element of the kernel can be written as a unique linear combination of these guys. Okay? Alrighty? Let W1 through WS, that's not a 5, that's an S, WS be a basis for the image now. Okay? So these W's are coming from what? W over here, right? Okay? Now, there exist vectors V1 through Vs in V such that T of Vi equals Wi. In other words, since these guys, what I'm saying here is since these guys are actually in the image space, okay, there's got to be at least one pre-image vector for each of these such that T maps that vector onto the corresponding W. So I'm mapping then T of Vi is Wi for I equals 1 through S. Okay? Alrighty. Where are these, by the way? Okay, these are pre-image vectors, so they're in V. Okay? I just said that, but re-emphasize here. Now, do you see I've got these vectors in the subspace V, and I've got this set of vectors in what? The subspace V. And I'm going to throw them together into one big set. I'll take their union, U1 through UR and V1 through VS, and I claim this is a basis for V. Okay? This is a basis for V. Now, let's remember the dimension of V should be what? Is supposed to be M. We called it M. So if this actually is a basis here, there should be a total of how many vectors here? There should be a total of M. Okay? Since I've got R of these, because I counted from 1 to R on the U's, and then what, 1 to S on the V's. We somehow have to show that R plus S is equal to M, or that's our conclusion, what it will be, and that will establish this guy right there, okay? So I'm going to show R plus S is equal to M. Okay, now how do I show it's a basis? Okay, two things. You need to show a basis, right? I need to show that it spans the space, right? What does that mean? That means every element of cap V here can be expressed as a linear combination of vectors from this set, okay? Not necessarily unique right now, I'm just saying span. Okay, to actually show uniqueness, we're also going to show afterwards what? That it's, let's see, I've got here, linearly independent. Those set of vectors are linearly independent. Okay, that would make it a basis, right? A basis is a set for a vector space is what? A linearly independent set that spans the space. Okay, let's do the spans part first, though. Okay, now I'm going to let V bar be an arbitrary element of cap B. Okay, so just grab any old one you want. Okay, I'm going to show that I can actually get that as a linear combination of these guys. Now here, let's do the following. T of V is certainly in the image of T, right? Okay, T of V bar is certainly in the image of T. Okay, now T of V bar is actually the following. In the following way, it's a linear combination of T of V bars here. Okay, because what? These guys were a basis for the image of T. Okay, so it's got to be expressed as some linear combination of those vectors. Okay, so I say for some scalars A1 through AS. Okay, ready? But T is a linear transformation, so we're going to play a little magic here. Okay, I'm going to imagine subtracting this guy on both sides, and notice that I could actually take the T, because it's a linear transformation, I could take the T on the outside here, okay, move it on the outside of this the summation, and then I could actually, because it's T on both of these, I could move it outside the V bar and the summation. So in other words, I claim this is just a rewriting of the difference between these two, right? Because of that linear combination. So when I subtract this guy on both sides, I get the zero vector over on this side, and then I can sort of quote-unquote factor out the T. Okay? By the way, if you remember originally, I said that property was sometimes called distributive in the past, okay? Because it almost acted like the distributive property. Okay? Anyway, so do you see that these are saying the same thing? Okay, these two. Okay? But wait, this vector is certainly in V. I mean, the vector that's inside the parentheses there, that's certainly a part of V, like cap V subspace. T of that vector is 0, so what can we say about that vector there? This vector has to be part of the kernel. Okay? That's got to be part of the kernel. Alrighty? Alright, so let's keep that in mind there. Now, since it's part of the kernel, this vector must be expressible as what? A linear combination of the basis vectors of the kernel. But what was the basis of the kernel? Oh yeah, it was the U's up here. Let's come back up here. Remember, this was a basis for the kernels? Okay, so that means there's got to be what? Scalars B1 through B, oops, that should be an R right there. Oops, typo. BR, such that, what? My V minus the summation there, that vector, is actually a linear combination of the U's, okay? J goes from 1 to R, So I'm using different indices in each case, right? But then I can notice here, I could actually isolate v bar, my original vector, by moving the summation back over to the other side. And you see that I have what? V expressed as a linear combination of the u's and the v's. Okay? Well, v was arbitrary, right? It was from cap v, but it was otherwise arbitrary. Okay? But I've clearly expressed that arbitrary v as a linear combinations of the u's and v's. So that means what? The u's and v's must span the space v. Okay? Now, let's do the next thing. Okay? To show it's a basis, I also have to do the following. The set of vectors here, all right, these guys is what I'm referring to. I want to show that those are linearly independent. Okay? Now, how do you do that? How do you show a set of vectors as linearly independent? Well, you have to show that the only possible linear combination of those vectors being the zero vectors is what? The zero vector is if all those what? All those scalars are zero, right? Okay? No other way to get zero out of those vectors except what? All the scalars have to be zero. Okay? All right. Now, but just suppose that's the zero vector. Okay? Certainly we could get the zero vector out of that if those are all zeros, but maybe there's some other way to do it too. Well, I'm going to show you no, there's only one way to do it, to make all those zero. Now what I'm going to do is apply t to both sides here. Now, you know that t of 0 is 0, I hope. Okay, can you see any linear operator operating on the zero vector better give you the zero vector out? Okay, if you don't see that's obvious, take that as an exercise for you. When I take t of the left-hand side, again, because it's a linear operator, see how I can, because it's summative and I can, sneak it all the way down to the vectors, right? Okay, so I rewrote, taking t, so I took t of this side. I took t of each side, actually, and got 0 on this side, of course. I've got that there. When I take t of this linear combination here, it's actually what the linear combinations of t acting upon the vectors. Okay? Oh, wait. The t acting on the uj, each of the uj's, u sub j bar, I should say, is the zero vector for each j, right? Why? Because remember the u's were actually what? A basis for the kernel. Okay? So all those guys are getting mapped to 0. Okay? So the above becomes what? Simplifies down to this. I've only got the v's left. Okay? I've only got the v's left. Now, remember that these were actually what? What's t of vi? That's what I was called wi. Those were actually what? A basis, right? A basis for what I was calling the image. All right? Well, if they're a basis, they have to be linearly independent. So the only way this can be 0 is if all the, what? A's are 0. Okay? So there we go. Since that's a basis for the image. Okay, so now we know all this argument here has shown what? With the t, okay, I've shown that the a's have to be 0. Okay? So up here, I've showed that all the a's have to be 0. Oh, I should come back up here. I've shown that all these a's here have to be 0. All those a's. Okay, I'm still not done. I have to show that the b's have to be 0 too. Okay, what am I going to do there? Okay, well, if all those a's are 0, then what we've actually got down is this situation here. Okay, so that linear combination is equal to 0. Okay, but then these b sub j's are 0, since what? Wait, the u's are a basis for the kernel. Okay, so these are linearly independent, so that means the b's have to be 0. Okay, thus the a's and the b's both have to be 0, so that means what? If all these scalars have to be 0, then these vectors that I showed you up here, the u's and v's together, are linearly independent. Okay, so they are a set of linearly independent vectors that span V, and they form a basis for V. Okay, now we said of here then, that means what? The dimension of the kernel we know was what? Here's the basis for the kernel. There's R of those. Okay, and then the basis for the image. Well, how many were there? There were S of those. And the dimension of the whole vector space cap V was M, so that we've got this. Okay, so R plus S is equal to M. And rewriting that, that means the dimension of the kernel of T plus the dimension of the image of T must be M, the dimension of V itself. Okay, so there you go. I hope you understood all that. Okay, you should be able to do those problems in that section now.